Hello everyone, welcome back to the channel. Now in this video we are going to implement a great algorithm, that is quicksort algorithm. Okay. Now the algorithms that we implemented so far, right, including bubble sort, insertion sort, selection sort, merge sort, and this quicksort, all these are comparison algorithms. Okay. And except for this merge sort and quicksort, the time complexity was O of n square, that was quadratic time complexity, right? Now, but for this one merge sort and quicksort, the time complexity is n log n. Okay, that is linear logarithmic time complexity. Quicksort is one of the best algorithm for sorting so far. Okay, because of its time complexity, and you don't need any extra space for quicksort. Okay, now I guess we are good to go ahead with the implementation. Let's start with the implementation of quicksort algorithm. Okay, we have created the method quicksort, but we actually going to do it in a recursive way. For that we'll need start index and end index as well. Let's create that method for now. Numbers 0 is our first index and numbers dot length -1 is our last index. Okay, let's create that method now. So in this method what we are going to do, we will have our start and end index as usual. Now this is where we are going to write our recursive logic. Now first what we need to do, first we are going to calculate the boundary. Okay, this boundary will tell us the correct position for the pivot element. Okay, now this quicksort algorithm worked on a concept of something called as pivot. Okay, with every single partition what we do, okay, with every single iteration what you do, you assume first of all, okay, that your last element is the pivot element. Okay, then in that particular first iteration you try to figure out what is the correct position for this particular pivot element. Okay, so after you're done with the first iteration, right, you know that you have figured out the correct position for this pivot element and you no need to change the pivot element position. Okay, so when you do that, you go through something called as partitioning. That partitioning tell us, okay, this is the, let's say this is the correct position of the pivot element, and before the pivot element, once you're done with the first iteration, right, before the pivot element you will have all the elements which are less than the pivot element, and after the pivot element, that is on the right side, you will have all the elements which are greater than the pivot element. Okay, so let's create that method and implement that logic of partition, which will take number, start and end index again. Let's create that method. Okay, what this is going to take again our start and index and the array. So let's implement what we discussed right now, right? Let's consider, first we are assuming that our pivot element is the last index value, that is numbers of end index, right? Now what you need, we are considering boundary that currently there are no smaller elements than the pivot. Okay, that is our assumptions basically. So for that we will take start -1, that means our left side array is empty. Okay, now you will take a loop, okay, that will start from start, it will go till end, and what you're going to do in this particular loop, you're going to check if your numbers of this particular element, basically that particular element, is less than or equal to pivot element. That is where you're supposed to do swapping. So if it is less than pivot, like we discussed, right, if it is less than pivot, you're supposed to move it before the pivot element, and that is what we are doing here. That means we figured out the element which is less than or equal to pivot element. That is what we are performing the swap in this particular array with that particular ith index, and we are increasing the value of boundary because we have taken this -1, right? We have considered that, okay, our left array is empty, that's why we are doing this pre-increment. Okay, and then after we are done with that particular loop, we will be returning the boundary, which is the correct value of pivot element. Now what you're supposed to do, you're supposed to sort the left side and right side of the array. For that we will be going with the same logic. We will be repeating this logic of finding the pivot element and again sorting the left side of the array and right side of the array. How do we do that? quick sort numbers start. So we already know that boundary, this pivot element position is final. Now that is not going to change. So what do we need to sort now? We need to sort boundary -1 and quick sort numbers boundary +1 till end. And we are missing our base condition. So let's write that if start is greater or equal to end, that's when you're supposed to come out of the recursion. And we are done with the implementation. So this is the logic for your quicksort algorithm. It is considered as one of the best algorithm for sorting. Even in Java, we have something called as dual pivot quicksort. Okay, this is just for the awareness purpose. Okay, just so that you know, this is the quicksort method implementation. Again, the time complexity is O of n log n, linear logarithmic. So what we are doing here, first we have taken a method, we have calculated the boundary, which is actually telling us the correct position of the pivot element. Okay, and how are we getting that particular position? That we have logic, we have written in this partition method. We have assumed that last element, whatever is there, right, that is our pivot, and boundary is start -1. Basically, currently there are no elements which are less than the pivot element. For that, figuring out what are the less elements which are less than the pivot element, right, we have written this loop, and we are checking if that particular index value is less than or equal to pivot, then only perform that swap and then return that particular position. And similar way you continue sorting the left side of the array and right side of the array. Okay, let's try running our program and see if our logic is correct or not. Okay, and we are getting the correct answer: 2, 3, 4, 7, 21, 63 and 66 and 82. So yeah, as you can see, we are able to get the correct answer. That's all I wanted to demo as part of this video. Now we'll be learning about 2 more sorting algorithms, that bucket sort and counting sort. That's all as part of this video. See you in the next one. May the source be with you.